Well, thank you everybody for coming out here on a cold October night. I'm glad to see so many people from our community here. I just wanted to say a thank you also to the interactions.org, which has inaugurated Dark Matter Day throughout the world. There's now, last time I checked, 150 sites around the world that are holding events today at the same time. So we're going to try to have some brief remarks, brief for a physicist remarks, where I hope we can give you a nodding acquaintance with the evidence that dark matter exists, and then discuss what our ideas about what the dark matter might be like, and how people around the world are trying to find it. This is, of course, going to be a quick overview, mainly meant to stimulate your questions for people who've been thinking about the dark matter who maybe don't work in that area. I will also introduce the panelists, well, first of all, when they arrive, if they're not here. But at the end of our prepared remarks, I will introduce them. And we'll start with Dr. Monika Lynker, who's going to tell us why we are so convinced that dark matter exists.
So this is my nod to Halloween. Thank you all for being here on Halloween. I'm going to very briefly introduce you to why we know that there is dark matter out there. And the dark matter that I'm talking about here is much darker than that cat that you see there. But what we mean by dark matter as a physicist is really matter that does not emit any light at all. And it was Fritz Zwicky who coined the term. Fritz Zwicky was a Swiss astrophysicist. He named the matter dunkle Materie, that's the German term for dark matter, and he did this based on observations of the speed of galaxies in a cluster of galaxies. The cluster of galaxies is called the Coma cluster of galaxies. And what he did is he observed how fast these galaxies were moving with respect to each other, and based on that observation of how fast they're moving, he calculated back how much matter there must be in order for them to stay bound together as a cluster. And I'll explain this in a little bit more detail in a moment here. But he came up with a much, much larger number of the mass of what the cluster had to contain than what he could see as visible light in the cluster. And so the term dunkle Materie, dark matter, comes from the fact that he said there must be more out there than I can see, basically. Here is a picture of the Coma cluster. So like I said, the Coma cluster is a cluster of galaxies. There's about 1,000 galaxies in this picture. So all of these light smudges that you see in that picture are actually galaxies, not stars. The Coma cluster, if you look at it, extends about the width of your thumb in the sky, the width and the length of your thumb. So there is, if you look in the sky and you look at that area of the sky, there's 1,000 galaxies there somewhere, somewhere back there. A galaxy is a huge cluster of stars itself, right? So in each galaxy there is a couple of billion to a trillion to, depending on how big the galaxy is, trillions of stars in each of these galaxies. So what Zwicky did was measure the speeds of these galaxies, and this is you can kind of think of this like in the solar system. So you know what the solar system, in the solar system we have all these planets that are circling the sun. They are doing that because of the force of gravity from the sun. So the sun, the force of gravity from the sun binds the planets in the solar system together. if you had something that was moving really fast coming into the solar system, that a comet or something like that, that comet would get deflected by the gravity of the sun. But the gravity of the sun might, depending on the distance where it is, might not be large enough so that it captures the comet. So it might just fly by and fly out of there again. And that's an object that is not bound then to the solar system and would not stick around. So in the same manner, these galaxies are all moving with respect to each other. And because they were moving faster than expected based on the amount of mass that there was, and with that on the amount of gravity, Zwicky was able to conclude that there must be a large amount of mass there that he couldn't see, that was dark enough that it did not emit any light at all. It's just the gravity that told him that it must be there. So this was in the 1930s that originated the term. A similar kind of logic was applied in the 70s by an astronomer called Vera Rubin and her collaborators. And what Vera Rubin did was she looked at the galaxies themselves. So what you see here on the picture is the Andromeda galaxy. That's the galaxy that is closest to us. It's very similar to our own Milky Way. And it consists of 1 trillion or so stars. And all of these stars are moving around the center of the galaxy. So here's the center of the galaxy, and we see this from our point of view a little bit edge on, but they are all moving sort of around the center this way. Our own solar system does that in our Milky Way as well. So if this was the Milky Way, we would be somewhere out here on the outskirts of the galaxy, and our whole solar system moves around the center of the galaxy. It takes about, I don't know, 200 million or so, a little bit more than 200 million years to get once around. So again, based on this relationship between the mass and with that the force of gravity that the center of the galaxy exerts, and the measured speed of the stars around the center of the galaxy, you can kind of conclude back what the speed ought to be, based on how much mass there is, how much visible mass there is, and then compare. And that's exactly what Vera Rubin did. So here is a picture of her, first of all, when she was at Vassar College as an undergraduate student looking through the telescope. What you see here is another picture of the Andromeda galaxy. This is out of their, her collaborator was Ken Ford, their 1970 paper. And these dark spots in here are the star system, or the stars where she took the measurements from. So each point on here is on the y-axis here you have the velocity with which these stars are moving, and on the x-axis you have the distance away from the center of the galaxy. And what you see is that when they're really close, the speed is not so large, then it rises, and then as you go further out, the stars that are further out, it looks almost like the speed is getting larger further out you go. Back there is a later paper that was the 1978 paper, where they had done the same kind of measurement for more galaxies, and we have since measured these same kinds of things for more and more galaxies. And we find consistently that the curves at the end here, where the stars are further out from the center of the galaxy, they are all what we call flat. So the speed as you go out does not decrease or increase, it stays the same. They are moving at the same speed. And that's not what we expect based on what we see from the visible light of the galaxies. What it looks like in the galaxy is that most of the mass is in the center of the galaxy, right here. And so it is sort of like the solar system, where most of the mass is in the sun, And when you think about the solar system, the Earth, which is closer to the sun, orbits the sun faster than Pluto, let's say, does, which is way out there. Pluto takes a lot longer to get around the sun than the Earth does. So what we would expect based on the visible mass distribution is that the speeds would decrease back here. So you would expect a curve that looks much more like this. And we don't see that in any of the galaxies. So the evidence here is that there must be more mass out there than we can see, again, just like with the Coma cluster that gave it a name originally. So I thought I'd take a few minutes to explain to you how we measure these speeds. Right? I referred to speeds of galaxies, I referred to speeds of the stars around the center of the galaxy. How do we even know how fast these stars are moving? And the way we know this is from the Doppler effect. So the Doppler effect, you might have heard about the Doppler effect maybe in terms of the sound. That's better known than the Doppler effect for light. But what you might have noticed is that if you have a source of sound, for example, a train that's blowing their horn, if you stand in front of the train, it sounds a little bit different than if you stand, hopefully you don't stand right in front of the train, right? So stand to the side of the tracks. It will sound different when it comes towards you than when it goes away. You hear this even more clearly when you think about a Formula One racetrack or something like that. When you stand in front and the cars are coming towards you, it has a higher pitch, and then when they go past you, it's a lower pitch, right? Yeah. So the reason why that happens is because in front of the source of the sound, the waves are scrunched together like this, and in terms of sound, that corresponds to a higher pitch, a higher frequency. And in the back of the source of the sound, they are stretched out, and that is a longer wavelength and a lower pitch in terms of sound. So light waves do the same thing. Light is also a wave, and when you have a source of light, like a star or a galaxy, and that star or galaxy is coming towards you, then in front of that source, all those waves will be squished together, so to speak, and in the back, when it's moving away from you, they will be stretched out. So the next question, I suppose, is how do you see this for light? How do you determine how stretched out or how scrunched together the light waves are? And the way we do that is by looking at light from a source, from a star, for example, and splitting the light up into its component parts. And that's where those slides that you have on the tables come in. So what you have on the table is a cheap kind of diffraction grating. And when you hold that up and look at the light, what you should all see is sort of a rainbow of colors, right? So that white light that is coming from the overhead lamps is actually blue light and yellow light and green light and red light and everything mixed together, and your eyes make white out of this. And you see this continuous spectrum from those kinds of lamps, but if you would look at a pure element, so if you would look at a gas that discharges light and the gas consists just of hydrogen or just of mercury or whatever element you have, what you see instead is a set of very distinct lines. So here's an example of the rainbow colors, and then there are these dark lines in between. And these dark lines correspond very succinctly to the particular element. So astronomers can actually tell what kinds of elements are out in the stars by looking at the pattern in the lines that the light from the star is emitting. And when Vera Rubin and her collaborators did their research, this is actually sort of a part of a figure in their paper. It looks like this. So this is kind of a little bit of a cartoon of this. A modern spectrum will look more like this. This is an example of a spectrum that one of my colleagues, Dr. Hinnefeld, took with the observatory that's up on Northside Hall. So here this looks different. The dark lines in there are dips in the intensity of the light curve. So going back to the Doppler effect, if this is your reference spectrum, if you know that these are the lines that are coming from, let's say, hydrogen, when the hydrogen is at rest in a lamp, like in the back of the room, you can look at that afterwards, then you know which wavelengths you would expect. And if in the spectrum instead these lines are shifted towards the blue corresponds to shorter wavelengths, then you know that that star, the source, must be moving towards you. And if it's shifted more towards the red, like this one here, they're shifted towards this side, and here they're shifted towards the blue side. When it's shifted towards the red, it's the longer wavelengths, and the source is moving away from you. And the more they are shifted, the faster they are moving away or towards you. So that shift in the wavelengths tells you how fast the star is moving or how fast the galaxy is moving, depending on what you look at. So that is both of the evidence that I told you before is based on this kind of an idea. There's a third evidence that I would like to mention here, and that is the bullet cluster. So this is another cluster of galaxies. And what you see in this picture is two clusters of galaxies. So visibly, there's a cluster here and there's a cluster here. It's a smaller cluster than the coma cluster. And the light in here is the pink is light that is emitted from gas, and the blue is colored in there is dark matter. And what we think has happened here is that the two clusters of galaxies collided. So you have this thing here that looks like a cone. That's why it's called a bullet cluster. The bullet went through this way, and the gas makes that shape, and the dark matter is here on the outside because dark matter doesn't interact with each other. It went right through. And so it ended up on the outside here. That's the original, where the original cluster was, and that's where the original, where the dark matter of the cluster that went through there ended up. And I have a simulation here where you can see how we think that this would have happened. So what you see here are these two clusters, these two blue blobs that are colliding with each other. They're going through each other. The dark matter doesn't interact with each other, so ends up on the front of the whole thing. The other dark matter stays behind, and it simulates pretty much exactly what you saw in the picture, in the previous picture, which was based on measurements. So, summary of what I talked about, the term dark matter comes from the observation of the coma cluster where there was missing mass that we couldn't see. The galaxy rotation curves gave the more exact evidence for dark matter. The bullet cluster is another indication that there is actually dark matter around. There's other evidence, and that includes the microwave background. So the microwave background is what we see from the very early universe, the radiation that's left over from the very, very early universe, and the way that large-scale structures, so clusters of galaxies are formed that could not have happened the way it did without dark matter either. And I'm not going to go into the details here. Instead, I leave the stage to you to tell us what it is or what it might be.